Everyone, my name is Sandoval, and today we'll be talking about exponential growth and decay models. So, exponential growth and decay models are usually used in natural applications, which include population growth, compounded interest, half-lives, and what we're going to be focusing on today, which is radioactive dating and radioactive decay. So the problem we're going to be working on deals with exponential decay. The spent fuel of a nuclear reactor contains plutonium-239, which has a half-life of 24,000 years. If one barrel containing 10 kilograms of plutonium-239 is sealed, how many years must pass until only 10 grams of plutonium-239 is left? So the first thing you're going to want to do is write down the main points or highlight the main points in the question. In this case, we have the half-life, which is 24,000 years, as stated in the question. Our total, which is 10 kilograms. And what we want to know how much time will pass before it gets to 10 grams. So to solve the question, the first thing we're going to use is exponential decay model, which is y is equal to y0 e to the power of negative kt, in which case y of 0 is the initial amount or the state, and negative k is the decay constant, and then t is the time. In this case, we're using the decay constant because the amount is decaying over a period of time. Now, a half-life, the equation for a half-life is the natural log divided by 2. But how do we arrive to this equation? Well, you have to refer back to your exponential decay model, in this case, the formula that I introduced before, and use that formula. Then you divide it by 2 since you're finding the half-life. Once you get there, you divide both sides by y of 0, which is our initial state, and you end up with 1/2 is equal to e to the power of negative kt. You find the natural log of both sides. In this case, that would cancel out the e. And because the natural log of 1/2 is negative, the natural log of 2, and you're left with the negative kt since you got rid of the e, you're left with the half-life, or t in this case, is equal to the natural log of 2 over k. In order to solve for this question, which is actually asking for the t, you need to find what your actual decay constant is. So you're going to have to solve for k. If you refer back to this question, all you have to do is rearrange the variables. So k would be equal to ln of 2, or the natural log of 2, divided by the half-life. And then you rearrange that using the values that you were given originally in the question, which is that the half-life was 24,000 years. And by simply doing a simple calculation, you arrive at this value, which you can then put into scientific notation, and it's equal to negative 2.9 times 10 to the negative 5th. Now that you can actually get to the math portion of it, where you are going to be solving for the t, or the time or the number of years that must pass before you get to 10 grams, you refer back to your exponential decay model. In this case, 10 grams is equal to 0.01 kilograms, since that's what the question is originally given to you in. So then y, 0.01, is equal to 10, which is our initial amount, y0, times e to the power of negative 2.9 times 10 to the negative 5th, which is our k, or our decay constant, times t. You divide both sides by 10, and you arrive at 0.001 is equal to e to the power of negative 2.9 times 10 to the negative 5th t. You find the natural log of both sides, and in such case, all you have to do is simply divide both sides by negative 2.9 times 10 to the negative 5th, and you arrive at that the time is equal to 239,000 years, which then you can rewrite as in scientific notation to make it much simpler to 2.39 times 10 to the 5th years. So 10 grams of plutonium-239 will be left after around 39,000 years pass.